All right, I've had a request to do problem number 25 in chapter 10. There is an unstable particle called the sigma minus, which can decay into a neutron and a negative pion. The mass of the sigma minus is 1,196 MeV per c squared. The mass of the neutron is 939 MeV per c squared, and the mass of the pi minus is 140 MeV per c squared. Write the equations that could be used to calculate the momentum and energy of the neutron and pion. You do not need to solve the equations, which would involve some messy algebra. However, be clear in showing that you have enough equations that you could, in principle, solve for the unknown quantities in your equations. It's advantageous to write the equations not in terms of V, but rather in terms of E and P. Remember, E squared minus PC quantity squared is equal to MC squared quantity squared. All right, so this is similar to what we have seen in our notes and in the book. All right, so you don't need to actually solve your result, but you do need to apply the energy principle and the momentum principle to describe this particular particle interaction. So essentially, we have our unstable sigma minus decaying into a neutron plus a pi minus. All right, so we've been given some masses. The sigma mass is equal to 1,196 MeV per c squared, and the mass of the neutron is equal to 939 MeV per c squared, and the pi minus is equal to 140 MeV per c squared. Now, a couple assumptions that you want to make. So you're not told otherwise, so this is fine to do this. You want to assume that the sigma minus is at rest, and this leads you to a really nice arrangement. So that means the initial state is that there's zero momentum, and therefore momentum is conserved. So the initial momentum equals final momentum, always true. In this case, they must both equal zero. Okay, so now we're going to go after decay. All right, so we'll start with the momentum principle. So when starting a problem like this, you want to just start with what you know. So we know that the momentum of the system is going to be zero. And in this case, so what we're looking at here is just after the decay has happened. So the neutron, momentum of the neutron plus the momentum of the pi minus must be equal to zero. Maybe they're at rest, maybe they're going in directions and velocities that would cancel each other out when multiplied by their mass. We don't know, but we do know that it will sum to zero, which is the important thing. From here we can see the magnitude of the momentum of the neutron must be equal to the magnitude of the momentum of the pion. So that's a solution to that. All right, we can't go any further with the momentum principle, so cool. Now we can move on to the energy principle. We have also found a useful equation. I'll square it to make it super clear. So the change in energy of the system is equal to zero. So this is, we've not been given any indication. It's not a closed system, so we're going to assume closed for the time of interaction. Very reasonable assumption with particle physics. So we have energy initial is equal to energy final. So we would have, it starts at rest, E rest of sigma minus is equal to the energy of the neutron plus the energy of the pion. We don't know whether or not they're at rest. That's one answer, but that may not be the right one. Okay, so from here we have m sigma minus c squared is equal to En plus E pi minus, and En plus E pi minus is equal to 1,196 MeV. So in this case, you would plug in the mass, which we were given at the beginning of the problem, and we would see that that c squared cancels that c squared. So now we have another useful equation. All right, we can keep going. So momentum and energy. And energy for the neutron are related. So En squared minus Pnc squared is equal to Mn c squared squared. Okay, so we know what this is for the neutron, so we can then say En squared minus Pnc squared is equal to 939 MeV quantity squared, and then it would follow for the pion, the pi minus particle. So the energy of the pi minus minus the momentum of the pi minus, c squared is equal to 140 MeV quantity squared. And now we have our 4 equations. And we could use these equations along with to go after our unknowns. There you have it.